Hi, welcome to the paper entitled Target Robust Discriminant Analysis here at the International Workshops on Statistical, Structural and Syntactic Pattern Recognition. I'm Wouter Kouw. This has been joint work with Loog. We're from the TU Delft and TU Eindhoven in the Netherlands. So I'm first going to sketch you a problem setting, and then I'll talk you through the design of an estimator and then some statements that we make about this estimator. So this concerns a domain updation problem setting. So suppose someone gives you a data set that they want you to classify, but they've not given you any labels. But they say, well, we have this other data set that's somehow related and that has been labeled. So maybe you can make use of that. So this we'll refer to this as a source data set. You decide to use this, and so your client tells you that there's some relationship between these two domains, but as you can see here, they're clearly different biased samples from some underlying data generating distribution. You can see they're shifted in feature space. Still, you decide to train a classifier on this labeled dataset, which you can see here. This black line is a decision boundary, and even though it fits nicely to the source data, it clearly doesn't fit very well to the target dataset. It just cuts it off quite high. So you decide to make an assumption on the relationship between these two domains. So how were they sampled from this underlying distribution, and maybe we can expect a certain kind of shift. So maybe it's just a shift in the x1 feature. So you make this assumption, then you train a fancy domain adaptive classifier. So if your assumption is correct, then you might see a substantial improvement over this source trained classifier. You can see that here. That's this dotted line. That's the adaptive classifier, and it has a smaller error rate than the initial source classifier. However, you had to make an assumption, and if your assumption turned out to be incorrect, such as in this scenario, then your adaptive classifier might actually perform worse than your source classifier. So you spend all that effort and then you actually get a worse result than your naive initial solution. Now you might think this is a constructed setting, but this actually happens quite a lot in practice, that you design some fancy domain adaptive classifier and it doesn't improve over your silly initial source classifier. And that has a lot to do with the fact that you are always, in this domain adaptation setting, if you don't have any target labels, you are always forced to make an assumption, and there's just no way of checking whether your assumption was correct or not before you're given any target labels. So we asked ourselves in this paper, can we design an estimator that will always improve over the estimator based on the source data? The answer is yes. We're calling it the target robust estimator. I'll talk you through. So this is the main statement in the paper. We propose an estimator for the target domain, specifically for discriminant analyses, whose empirical risk is strictly less than the risk of the source estimator on the given target data. So there's a lot in this statement. Let me just unpack it a bit. Our hat here is the empirical risk, so specific to the discriminant analyses models. So that actually means the average negative log likelihood. Theta hat S is, we'll get to that in a minute, that's the estimates on the source data. Z are the target samples, and then U are the target labels. So what we're seeing here is the risk of the source estimates on the target data. And what we're saying is that we have found a estimator, which we're calling theta hat T, which will produce an empirical risk that is going to always be smaller than that of the source estimate. So we're always going to see an improvement over the initial source estimator. Yeah, so let me just rewind a bit. Suppose we have source data X and Y and target data Z and U. The target labels U are unknown and must be predicted. So your source estimator is the set of parameter estimates obtained from minimizing the empirical risk with respect to the labeled source data. So X and Y are the labeled source data, and then this is the empirical risk of the discriminant analysis model, and then we minimize with respect to these parameters producing these source estimates. And so it's a discriminant analysis model, so the empirical risk is the average negative log likelihood of a Gaussian fit to each class. And so theta represents the proportion, mean, and covariance matrix of each of the Gaussians. So if we had these target labels U, we could measure the risk of the source estimator on the target data. So that's what you see here. That's the source estimates, target samples, and then these target labels U. And then we measure the empirical risk by plugging them into this function. So with this, we could design an estimator that never performs worse than the source estimator. So that's this difference in risks. So basically, we still have this this empirical risk, the empirical target risk of the source estimates, but we use that to subtract from this empirical risk of a free set of parameters theta. And then we form this minimization procedure. So what is actually happening here? This minimization procedure is going to try and find a set of values for theta here, which is either going to produce a smaller risk, so a negative number in this subtraction, or it's going to recover theta hat s, in which case the subtraction would be 0. Yeah, these risks will be equal. Values for which this risk is larger are simply not valid solutions to this minimization procedure, because theta, this free theta, and theta hat s are both part of the same parameter space theta, capital theta. So you could always recover theta hat s. Since we don't have target labels U, we should actually prepare for the worst. So this is the empirical target with respect to the actual true labeling. But we don't have that, so we can swap that out with the hypothetical labeling Q, and then keeping these parameter estimates fixed, we can maximize the target risk with respect to this hypothetical labeling Q, which is going to produce the worst case scenario for this given set of parameters. So that'll be the worst case labeling. So applying this worst case setting to the difference in risks gives us our target robust estimator actually. That's this theta hat t. And so what you can see here, it's trying to find a set of parameters theta, which is going to produce a smaller risk on the given target samples labeled with some worst case labeling Q. And so it's either going to find a smaller risk, which will be a smaller risk for the true labeling as well, because if we can find something for the worst case setting, that means it's we've also found something for a better setting. Or it's going to recover theta hat s. And so what we actually show in the paper is that in the specific case of discriminant analyses models, the equality, the fact that you're able to recover this theta hat s, is just that occurs with probability 0. We're going to always get a better estimate or a smaller risk. This is let me just sketch. So it's a substantial proof, but let me just sketch the underlying steps. So in discriminant analyses, the parameter estimates based on sample averages. So the proportions are based on the average labels, and then we have means, which are sample averages, and then the covariance matrix is the square deviation from the means. To produce exactly the same parameter estimates, theta hat t and theta hat s, the sample averages for the source and target data would have to be exactly equal. So you have two sets of samples, one from the source domain, one from the target domain, and their averages in feature space have to be exactly equal in order to get this setting where the target robust estimator will not improve. And so if we have continuous distributions or probability density functions in feature space to sample data points from, then this event occurs with probability 0. And so we can say that the target robust estimator will almost surely produce a lower risk on the given target data. So some discussion points. The target robust estimator does not depend on any domain shift assumptions. We don't use covariance shift or load joint domain error, if you're familiar with these terms. The results are only valid for empirical risks. So in the case of discriminant analyses, that means average negative log likelihoods. They're not valid for error rates. and that is because there's not a one-to-one correspondence between the error rate and a surrogate loss function. So the results are only valid for the given target data. They're not valid for future target samples. We're not generalizing to the target domain. We're making statements about the given target samples. Hence, the target robust estimator is transductive in nature. And so the limitation or the caveat here is that if your source estimator performs below chance, then there is no guarantee that your target robust estimator will perform above chance. There is a guarantee that it will improve over the source estimator, but that might not be substantial enough to push it over the chance level boundary. At least not without additional assumptions. At this point, you could introduce additional assumptions such as covariance shift or low joint domain error in order to guarantee this improvement above chance level. But that's not in the paper. That's a future work thing. Right, so thank you for your time. My name is Wouter Kouw. I'm with the Signal Processing Systems group at TU Eindhoven. This has been joint work with Loog, who is part of the pattern recognition lab at TU Delft. So I've sketched you the problem setting, I've sketched you our estimator and our main claim, our main statement in the paper, and the steps for the proof for that statement. If you're interested in more, the paper contains a lot more information and explanation, as well as experiments and more discussion points. So yeah, please have a look and enjoy yourselves.